Hello everyone, and welcome back to Math 220A Mathematical Logic. Lecture 18, Spaces of Types. Let M be an L structure in some language L, and let A be a subset of M. Last time we have introduced complete types, so recall that a complete n-type over A in M is a set of LA formulas P of x1 through xn, so all the LA formulas in free variables x1 through xn, such that P of x bar together with the complete theory of M and parameters for A named is consistent. So this just tells us that P of x bar is a type, and moreover, such that for every formula with parameters from A, phi of x bar with x bar a tuple of the same variables x1 through xn, we have that either phi of x bar is in P or the negation of phi of x bar is in P. And we have introduced the collection of all complete types. So recall that Sn A M is the set of all complete n types over the set of parameters A in a given structure M. So today we will introduce a topology on this set of types, turning it into a topological space with nice additional properties. So for a formula phi of x1 through xn, an LA formula we will let square brackets phi be the set of all complete types in over this given set of parameters A, such that phi belongs to P. Note that if P is a complete type and we have that the formula phi disjunction psi is in P for some formulas phi and psi, then we have that phi is in P or psi is in P. So this follows by completeness of the type. So we have that the corresponding set given for the formula phi or psi is exactly the union of the set corresponding to phi and the set of types containing psi. And 2, similarly, we have that the set of those types which contain phi conjunction psi is exactly the intersection of the sets of types containing phi and the set of types containing psi. This shows that the sets of this form, square bracket phi for some phi, are closed under unions and intersections. And now we define the stone topology on the set of complete n types over A to be the topology generated by taking the sets of the form phi, where phi is an LA formula, to be the basic open sets. So you take the topology generated by these sets. So this means that open sets are exactly the unions of possibly infinitely many sets of the form phi for different phis. We begin by summarizing some of the basic properties of such spaces. So, remark, for a complete type P, an n-type, let's say, over A, we have that exactly one of phi and not phi is in P, because it has to be consistent, so it cannot contain both. By completeness, it contains at least one of them. Thus, we have that the set of all types containing P is exactly the whole space, so the set of all types, minus those types which contain the negation of phi. And so we see that this complement of the set is also closed. So this shows that any set of the form all types containing phi is both closed and open in the topology we just defined, and we refer to such sets as Clopal sets. We have the following lemma. 1. The space of types is compact. And 2. The space Sn of A is totally disconnected which means that if we have two types, PQ, 2 points in this space, which are distinct, so P is not equal to Q, then there is a Clopal set X such that P is in X and Q is not in X. This of course implies that in particular the space of types over A is Hausdorff. So recall topological space is Hausdorff when given any two distinct points we can find a pair of open sets containing each of them and not intersecting. In this case, the Clopal set X is in particular open, and the complement is also open since X is also closed. So this gives us a pair of sets separating the points, but in fact it gives us this much stronger condition that any 2 points can be distinguished by a Clopal set. It's a very strong form of disconnectedness. Proof 1. To demonstrate compactness of the space, it suffices to show that every cover of the whole space by basic open sets has a finite subcover. So indeed, the topology is generated by the basic open sets. So every open set is a union of the basic open sets. Hence, if we have an arbitrary cover of the space by open sets, we can write each of these open sets as a union of the basic ones. And so we obtain a cover of the whole space by basic open sets. And so indeed it would be enough to show then that it has a finite subcover. So to see this, suppose not towards a contradiction, and we let C witness it. So we let C be a cover by some sets of the form phi I of x bar for I in I, an arbitrary index set. So let this be a cover of the whole space by basic open sets with no finite subcover. We let gamma be the collection of all formulas of the form not phi of x bar for I in I, so the negations of all of the formulas that appear in the basic sets in C. Now we claim that gamma, together with the theory of M in the language with the parameter for A named, is satisfiable. As usual, to show this, it's enough to check that every finite subset is satisfiable. So assume that I0 is a finite subset of I, the index set. Then, because we're assuming that there is no finite subcover of C, there must exist a point in the space, so a type P in SNAM, such that P is not in the union of the sets in this finite subcover. So it doesn't belong to the union of phi I for I ranging over I0. Now let N be an elementary extension of M containing a realization A bar of P. Remember last time we have proved that every type can be realized in an elementary extension. Then we have that N satisfies the A theory of M, where all the constants are interpreted by the elements that they represent, because N is an elementary extension. And it also satisfies the conjunction of not phi of A bar for I in I0. Because by assumption, this type does not belong to any of the sets phi I for I in I0, so it means it contains the negations of these formulas. So realization of P satisfies this, but then this shows that gamma is finitely satisfiable and so by compactness actually satisfiable. Now let N be an elementary extension of M, and let a bar in N realize gamma, so all of gamma this time. Then we have that the complete type of a bar over A in N belongs to the space of complete types over A in M. So remember, when A is a subset of M and N is an elementary extension, then the complete types over A in N, or in the sense of M, represent the same set. So we have that the type of a bar over A belongs to the complement of all sets of the form phi I of x bar for I in I. So we have found a point which is not in the covering, in the supposed covering C of the whole space. So this is of course a contradiction. So we have shown that the space of types is compact, and in fact this is exactly where the term compactness comes from in the compactness theorem of first order logic. So we see that compactness theorem corresponds precisely to the compactness of the spaces of types. And to see the second claim, that the space is totally disconnected, assume that we have 2 points, P and Q, which are distinct, so 2 types over A, 2 complete types over A. Then by definition of types, for them to be distinct, it means that they're distinct as sets of formulas. So this means that there is a formula phi in LA such that phi belongs to P and the negation of phi belongs to Q. So any 2 complete types must be distinguished by some formula. But then we have that the basic Clopal set containing all types containing phi is a basic Clopal set containing P but not Q. So we get a Clopal set separating the 2 types. This shows total disconnectedness. The next lemma shows that natural operations on types often give rise to continuous operations on the corresponding type spaces. More precisely, 1. If we have that A is a subset of B, both subsets of M, where M is an L structure, and assume that we have a type P over B in M, we define P restriction to A, a smaller set of parameters, to be the set of all LA formulas in P. So we keep all the formulas with parameters from A that are in P and ignore all the other parameters. Yeah? So then we have that P restriction A is itself a complete type over A, and the map which sends P to its restriction to A is a continuous map from the space of types over B onto the space of types over A. 2 if f from m to n, so n is also an L structure. So if we have f, an elementary embedding, and P is a complete type over A, we define f of P to consist of all formulas of the form phi of x bar f of a bar, where f of a bar is the tuple of the form f of a1 through f of an, such that phi of x bar a bar is in P, and A is a tuple from the set capital A, then with this definition we have that f of P is also a complete type, but now in N, over the image of the set of parameters capital A, and we have that the map that sends P to f of P is continuous. And 3, if we have f from A to N is a partial elementary map, then Sn of A is homeomorphic to the space of n types in N over the image of the parameter set capital A. Proof 1. Note that we have that P restriction to A together with the A theory of M is a set of formulas that is a subset of those formulas which are in P union the B theory of M, because B is just a larger set of parameters. So it particularly contains all sentences with parameters from A that hold in M. So we have this containment, and we know that the larger set is satisfiable by the assumption that P is a complete type over B. So then we have that P restricted to A together with the A theory of M is also satisfiable. And because we have that P restricted to A by definition is the set of all LA formulas in P, we have that P restricted to A is complete because P was complete. So in particular, for every A formula, either phi or not phi is in P. And we have that if phi is an LA formula, then the set P, the set of all types P, in the space of complete types over B, such that phi belongs to P, is equal to square brackets phi, a basic, let me write subscript B to stress that it's a basic open set in the space Sn of B in M. And so this shows that the preimage of a basic open set in the sense of the space of types over A under the map that sends P to its restriction over a smaller set of parameters is itself the basic open set square brackets phi B, so all types over B that contain phi. So we see that the preimage of an open set is open on the basic sets, and so of course it also extends to arbitrary open sets. So this shows that the map is indeed continuous. This proves 1. Let's show 2. Suppose that delta is a finite subset of the set of formulas f of p that we just defined. So say for definiteness that delta is of the form phi 1 of x bar f of a bar through phi m of x bar f of a bar for some formulas phi 1 of x bar a bar through phi m of x bar a bar all in P. Now, because we know that P is a complete type, so in particular P, by definition of types, P together with the A theory of M is consistent, we have that M satisfies existence of an element, so exists x bar, so that all of these finitely many formulas hold. So phi I of x bar a bar, simply because we know that the type has to be realized in some elementary extension of M, and so any finite set of formulas like this must be realized in M then. But also, as F is elementary, it preserves the truth value of the formulas. So we have that also N satisfies the same formula, exists x bar conjunction over all I from 1 to M, phi I of x bar f of a bar, and delta was an arbitrary finite subset of f of p. So any finite subset of f of p is realized by some element in N. So by compactness, we conclude that the set of formulas f of p, together with the f of capital A theory of N, is consistent. So this shows that f of p is a type, and we also see that it is a complete type immediately from the definition, because for every formula phi with parameters a bar, it either belongs to p or its negation belongs to p, as p was complete. And so for every formula in the set, we get the same, that either phi of x bar f of a bar or its negation belongs to p, to f of p, excuse me. So this shows that fp is complete. By definition. Finally, note that the set of all complete types P over A, such that phi of x bar f of a bar is in f of P, is exactly the basic Clopal set given by phi of x bar a bar, an LA formula. So this shows that the preimage of a basic open set in the space of types over f of a bar in N is itself a basic open set under the map sending P to Fp. Hence, we conclude that the map P maps to f of P is continuous. So this concludes the proof of 2, and we leave the proof of 3 as an exercise. In the future, we will be interested in a special kind of types which represent the isolated points in the space of types. Definition: we say that a complete type P over A in M is isolated if the set consisting of a single element P is an open subset of the topological space of types. This corresponds to the usual meaning of an isolated point in a topological space. So we have a neighborhood which so that the only point of this open neighborhood is the type P itself. We have the following proposition characterizing isolated types. So let P be a complete type over A. Then the following are equivalent. 1. P is isolated. 2. The set consisting of a single element P is of the form square brackets phi of x bar for some LA formula phi of x bar. In this case, we say, so when this equality holds, we say that the formula phi of x bar isolates P. And 3, there is an LA formula phi of x bar in P such that for all LA formulas psi of x bar, we have that psi of x bar is in P if and only if the A theory of M implies that phi of x bar implies psi of x bar. So modulo the A theory of M, all formulas in the type P are implied by this one single formula phi in P, and vice versa. Proof. First we show 1 implies 2. Assume that X is an open set, so an open subset of the space of n types over A. Then by the definition of the topology, we know that we can write X as a union of the basic open sets. So X is a union of the sets of the form square brackets of I for some formulas phi I for I in I, and these are LA formulas, of course. Now, if we have that the set consisting of a single element P is open, Hence, in particular, it is of this form, a union of basic open sets, but it's just a single point. So if the set is open, we must have that it is actually equal to just one of the sets from this union. So it's the set equal to the set square brackets phi for some formula phi. Yeah, because it's a single point in the union, so it belongs to one element of the union, and then we already get the whole set. Now we show that 2 implies 3. So suppose that the set consisting of a single element P is of this form, so it's equal to phi of x bar, all types containing phi of x bar for some phi. And suppose that psi of x bar is an arbitrary formula in P, then we claim that modulo the theory, the A theory of the structure M, we have that phi of x bar already implies psi of x bar. So assume not towards contradiction. Then there is an elementary extension n of M and a bar, a tuple from n of length corresponding to the length of the tuple of variables x bar, such that in n the implication is not satisfied. So we have n satisfies phi of a bar and not psi of a bar. As usual, we get this by an application of the elementary diagram method. But then we can take Q to be the complete type of a bar over A in N, which is also a complete type over M, of course. So we know, as usual, that types in N and in M over a subset of M are the same. So this is an element of the complete space of types over A in M. But now, because we have that phi of x bar is in Q, it follows that Q is equal to P, because P is the only element in the set square brackets phi, which by definition is all types containing phi. And we got that Q contains phi, so Q must be equal to P then. But we also have that the negation of psi of x bar is in Q, but this is a contradiction. Since by assumption psi of x bar is in P equal to Q. So we get a contradiction. So this shows that shows one implication, that phi of x bar implies psi of x bar. Conversely, if on the other hand we have that psi of x bar is not in P, then we have that the negation of psi of x bar is in P, and applying the same argument, we get that the A theory of M implies that phi of x bar implies the negation of psi of x bar, and because we have that the A theory of M together with a single formula, phi of x bar, is satisfiable, it follows that the theory the A theory of M cannot have phi of x bar implies psi of x bar as a logical consequence, because we get it's satisfiable both ways. So this shows the converse. So we have demonstrated that 2 implies 3. Finally, we show that 3 implies 1. So assume that phi is a formula in P satisfying 3. Then we claim that P is the only type containing this formula. So the set square brackets phi is exactly the set containing P as a single element. So first of all, we clearly have that P belongs to this set, because phi is a formula from P by assumption. Now suppose that we have some type Q in the same set, and let psi of x bar be an LA formula. If we have that psi of x bar is in P, then by the assumption 3, we have that the theory of M with the parameters for A named has as a logical consequence the formula phi of x bar implies psi of x bar, and we have that psi of x bar belongs to Q in that case, because phi belongs to Q. But on the other hand, if psi of x bar is not in P, then the negation of psi of x bar is in P by completeness of P, and by the same argument as above, we get that psi of x bar is not in Q. So then we have obtained if psi is in P, then psi is in Q, and if psi is not in P, then psi is not in Q. So the conclusion is that P is equal to Q. So we get 1. And this concludes the proof of the proposition. Let's give a description of the space of types in the case of dense linear orderings. So in this case, the language is just the language of orders. So let M be a structure, so a dense linear order without endpoints. And let A be an arbitrary subset of M, and let P be a one type over A in M. If A is an element of A, then because we assume that P is a complete type, we have that exactly one of the formulas x is equal to A, x is less than A, or x is greater than A has to be in P. So in the first case, P is realized in A, which simply means equivalently that the formula x equals A is in P for some A in A. So in this case, we have that P consists of all formulas psi of x such that M satisfies psi of A, and P is isolated by the formula x equals A, so it clearly determines all the other formulas that are satisfied on this element, if we know what A is. Case 2. Otherwise, so P is not realized in A. In this case, we can define two sets. So first LP, which consists of all A in A, such that the formula A less than X is in P. And we also define the set UP to consist of all those A in A, such that the formula X less than A is in P. Note that if A less than X and X less than B are both in P, then as P together with the A theory of M is consistent as a type, we must have that A is less than B. Thus, we have that A is less than B for all A in the lower part, LP, and B in UP. And also we have that the pair LP-UP determines a cut in the ordering restricted to the set of parameters A. Also note that conversely, if we have that A is a disjoint union of a pair of sets L and U, and we have that A is less than B for all A in L, B in U, then the theory of M with parameters from A, together with all formulas of the form A is less than X, A is in L, and X less than B, B is in U, is satisfiable, because by density of the linear order, we can always, for any finite set of formulas from this set, we can always find the formula in between all the corresponding A's and B's. Thus, we have that there is a type P with LP equal to L and UP equal to U. So we claim that the cut completely determines the corresponding type. That is, that we have the set with a single element P is precisely the intersection over all A in LP, A less than X, intersected with all basic sets of the form X is less than B for B in UP. To prove this claim, suppose that Q and P are two distinct types, but LP is equal to LQ and UP is equal to UQ. But since we know that the only atomic formulas are of the form X is equal to Y, X less than Y, it follows that PQ determine the same cut in A and contain the same atomic formulas since the theory of dense linear orders has quantifier elimination. All quantifier free formulas are simply Boolean combinations of atomic formulas, So it follows that P and Q contain the same quantifier-free formulas, and hence they agree on all formulas up to logical equivalence. So by QE it follows that P is equal to Q. Using this identification between complete types and cuts, we can give a complete description of all one types over Q in the model of the DLO with Q with the base set Q. So namely, we can define P plus infinity to be the unique type P with LP equal to the whole set Q and UP equal to the empty set. Similarly, we can take P minus infinity, the unique type P with LP empty and UP all of Q. For R, a real number which is not rational, we can define PR be the unique type P such that LP corresponds to all rational numbers Q so that A is below R, and UP consists of all B and Q so that R is below B. And finally, for C, a rational number, we let PC plus be the unique type P with LP equal to the set of all A in Q such that A is less or equal than C, and UP consists of all B so that C is less than B. And similarly, we let PC minus be the unique type P with LP consisting of all A so that A is strictly less than C, and UP consisting of all B and Q such that C is less or equal than B. So for every element we can consider the cut immediately to the left of it, C minus, and the cut immediately to the right of it, PC plus. This gives all possible types because of the correspondence to the cuts. So in particular, we have that the number of one types over Q is continuum 2 to the Aleph naught. This analysis can be extended to the case of arbitrary models of DLO, which we leave as an exercise, but summarize the description. So let M be a model of DLO, A a subset of M, non-empty. Then we have that types, one types over A in M, not realized by elements of A, correspond to cuts in the ordering of A, induced ordering of A, and we have that a non-realized type is non-isolated if we have that either UP is non-empty and has no least element, or LP is non-empty and has no greatest element.